Hello, my name is Gerald Coe, and in this video I'm going to explain the instruction set and assembly language programming of the Avalanche CPU. But before we do that, let's have a look at the memory map. Avalanche is a Harvard architecture processor that uses separate instruction and data spaces. The instructions are all 32 bits wide and stored in a 2K by 32 ROM. In the Lattice HX8K FPGAs, this is built from 16 of the 4K RAM blocks. The CPU is a 16-bit processor. The registers, ALU and data path are all 16 bits wide. The 256 CPU registers are directly addressed from the fields within the instruction. I/O space from 100 hex to 1FF and the data space are indirectly addressed using these registers. Data RAM is 8 bits wide because that is a better use of the limited FPGA RAM resources, but it could easily be 16 bits if required. Okay, if we take a look at the instruction set for the CPU, the first thing we note is there's not very many of them. In fact, there are just 18 instructions. Some of those have got variations, and we've shown those variations here for the add instruction, but they also apply to the OR and an exclusive OR instructions. The instructions are 32 bits wide, and that comprises of an 8-bit opcode field, an 8-bit destination address, and two 8-bit source addresses. And those 8-bit addresses can access one of 256 CPU registers. So we can perform an operation on two registers and write the results back to a third register. Now the variations of these is that not only can we use the registers themselves, but we can also use the memory location pointed to by the register. And the same applies to source register 2. We can use the register itself or the memory location pointed to by the register. In the case of the OR and an exclusive OR instructions, we haven't shown those four variations, but they still apply. In the case of the SRL instruction, the destination register can be indirect, but RS1 cannot. By using the same address for the destination as the source register, you'll shift that register right by 1 bit. In the case of the clear bit and set bit instructions, RS1 is replaced by a 4-bit immediate value. This is the bit number in RS2 that you want to clear or set. Both the destination address and the source register 2 can be indirect, and in that way you can set or clear any bit in any register, in any port address or any data memory location with one instruction. In the case of the next four instructions, the RS1 and RS2 registers are replaced by a 16-bit value. This is the 8 high bits and the 8 low bits of the value. And in the case of the load immediate instruction, this 16-bit value is loaded directly into the destination register. In the following three jump instructions, this 16-bit value is a 16-bit target address for the jump destination. The assembler will put this value in from a label in your assembly program. The remaining 7 instructions all have the letter R following them, and this signifies that the target address for these jump instructions is the destination register. So this register needs to be preloaded with the target address before you execute these instructions. In the case of the JAL-R instruction, RD is the jump address and RS1 receives the incremented PC. The next four instructions all perform a comparison between RS1 and RS2, and if true, will jump to the destination address. The final two instructions do a bit test on the RS2 register. The bit is addressed by the 4-bit immediate value, 0 to 15, and if the bit is true, set or clear, jumps to the target address. RS2 can be indirect. This means that you can test any bit in any register, in any port address, or any data memory location. This is the complete instruction set for the CPU. The assembler does have some macro instructions built in to make life easier. But before we move on to those, we need to have a look at some special registers. The first three registers must be preset in the assembler to specific values. Register 0 must contain 0. Register 1 must contain the value 1. And register 2, the -1 register, must contain -1 or OXFF. The assembler and the macro instructions expect these three registers, these three CPU registers, to contain these values. So these must be initialized in your assembly file, and it must be the first three registers that you define. Now I'll show you that in a few minutes when we have a look at the assembly language. But first let's move on to the macro instruction set. You see here the first instruction is a no-op. Now the CPU doesn't actually have a no-op instruction, and what the assembler does is use an add instruction when it sees this. What it does is add the 0 register to the 0 register and writes the results back to the 0 register. Now 0 plus 0 is 0. So even if you could write to the 0 register, which you can't, this is definitely a no-op. The next two registers, increment and decrement, are actually add instructions behind the scene. And what they do is add the contents of the 1 register to the destination register, or they will add the contents of the -1 register to the destination register. And this has the effect of incrementing or decrementing the destination register. The JLER instruction is actually the JGER instruction, jump if greater than or equal. The jump if less than or equal macro is the same instruction, but the assembler will swap over the source 1 and source 2 register positions within the opcode fields, and that has the same effect. Likewise, jump if greater than is exactly the same as jump if less than. Again, source 1 and source 2 fields are swapped within the opcode. Now you're probably wondering why subtract is a macro instruction and not a native instruction. And the answer is to keep the CPU speed high. If we make subtract a native instruction, it increases the complexity of the ALU. And that increased complexity manifests itself as a greater depth of logic cells used to implement the ALU. And that greater depth of logic cells increases the propagation time and hence slows it down. The effect of that is to slow down every instruction, so the overall CPU speed is much slower. By using 3 instructions as a macro instead of 1, we keep the CPU speed high. Now subtract actually works by adding the 2's complement of RS2 to RS1. The 2's complement of a number is the 1's complement incremented, and the 1's complement is all of the bits turned upside down. In other words, it's exclusive ORed with OXFFFF. SSL, shift left logical, is actually an add instruction. It adds RS1 to itself, which has the same effect as shifting it left, and then stores the result in the destination register. DJNZ will decrement the target register and jump to the label address if it's not 0. The next 3 instructions all use the JAL or jump and link instruction. Jump to label uses the 0 register as the link register, and since this is not writable, it has no effect, so this is simply a jump to label instruction. Call uses the supplied RD as the link register and then jumps to the label. Return uses the JAL-R instruction. It returns to the address contained within the destination register and also uses the 0 register for its own link. And again, that is unwritable, so this is simply a return to RD. The next 6 instructions all compare RS1 with RS2 in various ways, jumping to the label address if true. These are all 2 native instruction macros. The final 2 macro instructions, jump of bit set and jump of bit clear, will test the specified bit in the RS1 register, jumping to the label if true. Okay then, so if we have a look at some assembly language code, we can see how it's all put together. A semicolon starts a comment. Everything from the semicolon to the end of the line is ignored by the assembler. To give meaningful names to constants, like OX100, you can use the .const directive. Here, LED port address is defined as being OX100. So every time the assembler sees LED port address, it will change it to OX100. The .data directive initializes or reserves space in the data RAM. This starts at OX200. Here you can initialize individual bytes. You can define an array of bytes which you will be using as a buffer. These are uninitialized. And you can also initialize a string. When you use a string in this way, there will be a 0 at the end of it, so it will use one more byte than the number of bytes in the string. Here you can see the first 3 registers being defined. They're given the numbers in order that they're defined, so the first one is register 0, register 1, register 2, and so on. These first 3 registers must be defined. Register 0, which we've called 0, is given the value of 0. Register 1, which we've called 1, is initialized to 1. And register 2, which we've given the name of -1, is initialized to OXFFFF, which is -1. You must do this as the first thing in your file. No other registers must be defined before these, so these must be 0, 1 and 2. You can define other registers after this. With Avalanche, you must have a minimum of 7 processors defined. This is because of the way Avalanche works. We cannot have more than one instruction from a particular process in the instruction pipeline at any one time. Doing so could create hazards of pipeline stalls, or worse still, a complete pipeline flush. By having a minimum of 7 processors defined, we prevent that. Indeed, Avalanche does not contain any mechanisms for dealing with pipeline flushes or pipeline stalls, so it's absolutely essential that you define a minimum of 7 processors. You can have more, but you cannot have less than 7. Here I'm going to define 7 processors, and my process is the first one of those 7. Now with those 7 processors, I'm going to assume that the processor is clocked at 70 MHz. At 70 MHz it will be doing 70 MIPS, and my process, which is one of 7 processors, will get 1/7 of that. In other words, 10 MIPS of processing power. It will be clocked at 10 MHz and it will execute 1 instruction on every clock cycle. The same applies to all other primary processors. If we move down, we find that process 2 has got a .A and then there's another process, P2.B. This is because the primary process, P2, has been divided into 2 subprocessors, A and B. When you do this, there isn't really a process called P2 anymore. There are simply 2 independent processors called P2A and P2B. And these are completely independent CPUs, just like my process is. These 2 processors will share P2's time slice of 10 MIPS. In other words, P2A and P2B will each get 5 MIPS of processing power. Likewise, if we split a process into 3, P3A, B and C, P3 gets 10 MIPS of processing power. So P3A, B and C will each get 3.3 MIPS of processing power. Again, my process, P2A, P3B, are all independent CPUs running their own program. The only difference is that the primary processing time is split between the 2 sub-processors. And here we find we've defined P4. There is just P4, so this gets 10 MIPS, P5 gets 10 MIPS, P6 gets 10 MIPS, and P7 gets 10 MIPS. When a primary process is split in this way, the primary process can no longer hold any code itself. The code is contained within the sub-processors. It's the time available to P2 that's being split between the 2. So when we say you must have a minimum of 7 processors defined, then that is primary processors, P2, P3, P4 and so on. You must have a minimum of 7 primary processors. One example where you're going to need plenty of processing power of a primary process would be, for example, scanning an array of WS2813 pixel LEDs. These will take 10 MIPS of processing power to do that. However, for something like a 9600 board UART, you'll find that 1 or 2 MIPS of processing power is all that you need. In this case, a 10 MIPS primary process could easily be split into 10 sub-processors, and you could have 10 UARTs running at 9600 baud with no problem. If you have a look at process P7, we find that there's 3 registers defined, A, B and X. Because these 3 registers are defined within process P7, they're considered to be local to that process. They're not visible outside of that to other processors. Within process P7, I've listed all of the native and the macro instructions available to the processor. Here you can see that we've also documented the number of native instructions used by each of the macro instructions. And you can see subtract is the most at 3 native instructions. Decrement and jump if not 0 uses 2, and most of the conditional jumps use 2. Okay, I've just taken this source file and run it through the assembler to generate a listing file, which I have just here. Now the first thing I want to have a look at is these 3 register definitions, and if we go to the listing, we can see that the assembler has assigned these the registers 3, 4 and 5 for registers A, B and X. Just commit that to memory for a few moments. 3, 4 and 5, A, B, X. So I want to scroll down and show you the subtract instruction. And as you can see, it's actually generated 3 separate assembly instructions, native instructions to do the subtract. And the first one is 04 is the opcode for exclusive OR. Then we have the destination register, the first source register and the second source register. Now 04, remember, is B. 3, 4 and 5, A, B and X. So register 4 is the B register, and we are exclusive ORing it with register 2. Register 2, remember, is one of our 3 predefined registers that we put on at the start of the program. Register 0 is 0, 1 is 1 and 2 is -1, or FFFF. So what we're doing here is exclusive ORing register B with FFFF. In other words, we're inverting all of the bits in register B, and we're storing the result in register 6. Now register 6 is worth a mention because we don't actually have a register 6. If we go back to the definitions, we have 3, 4 and 5, and there are no other registers defined. Register 6 is an assembler generated register. The assembler has assigned register 6 as the next spare register available. If we had defined another register, that would be 6 and the assembler would use 7. So when necessary, the assembler will assign itself a register to use for intermediate results. And that's what's needed here, because none of these can be changed. B, A, and the destination is X, so that's going to change, but A and B can't. So the assembler is generating a register 6 to use as an intermediate register. The next instruction, 00, is an add opcode. And here we're adding register 6, which is our new intermediate value, with the register 1. Register 1, remember, is the other predefined register and contains the value 1. So here we're incrementing register 6 by adding 1 to it and storing the result back in register 6. So register 6 now contains the exclusive ORed and incremented register B. In other words, the 2's complement of register B. So the final thing to do is to add it to A, and that's what we do here. 03, remember, is register A. We're adding 03, 06 and storing the result back in register 5, which is the X register. So by adding in the 2's complement of B, we are effectively doing a subtract, but we are taking 3 native instructions to do it. The assembler will not generate endless intermediate registers. If it's generated one, like in this case register 6, it will use it again and again as needed. So you can see these other subtract instructions also use register 6. If we take a look at the DJNZ instruction, we find this is actually made up of two native instructions. The first one, 0, 0, is an add instruction, and it's adding 0, 5, which is our X register, remember, and 02, which is our -1 register. So it's adding -1 to X. In other words, it's decrementing X and it's storing the result back in X. So that is a decrement X instruction. That's followed by a jump instruction. Now this 95 is the opcode for jump if not 0. And the register it's testing is register 5. So we've decremented register 5. Now we're testing it for 0, and if it's not 0, we're going to jump to this absolute address, 0009. And that is the address of my label. The assembler has put that address in for you. And if we look at my label, here we find indeed it is at address 0009. If we just have a look at one more, jump if equal, AB my label, compares A and B, and if they're equal, it takes the jump to my label. Now the first opcode is load immediate, and that is loading 0009 into register 06, which is the assembler generated spare register. So register 6 is being loaded with the target address. The next instruction, 99, is the jump if equal R instruction, and that is doing the actual comparison. It's comparing register 3, which is A, register 4, which is B, and it's jumping to the target register where register 6 is, if they are equal. What I will do is put this file, avsm.s, onto the Avalanche GitHub page, because it's a handy reference and you can see all of the available instructions. Okay, that's it for this video. If you'd like to play with the Avalanche assembler, it's available from our GitHub. And in the next video, I'll be showing you how to put it all together and use the Avalanche processor in your own Verilog projects.